Okay, we have a marble that has a mass of 0.1 kilograms, 2 meters above the ground, top of the first roller coaster hill. So, and I should say this, it's at rest. I think you'd probably assume that. So the mass is 0.1. We're going to use potential energy to find out how much energy it starts with. Gravity is 9.8. The height is 2 meters. So our potential energy at the top here is 1.96 joules. Just a quick note here. This would be a gigantic marble. Like, your marble is not going to be that big. So when you get these numbers for your actual roller coaster, just be aware they are not going to be as big as this. Okay, so how fast is it going when it hits the ground? Well, we're comparing two different positions here at the top and here at the bottom for one mass. So we're going to want to use that equation we always use. Ki plus Pi plus work equals Kf plus Pf. So let's plug some stuff in. So at rest plus 1.96 plus the work. Work is going to be 0 because they made a big point of saying there's no friction, no air resistance. It's not like the marble has a jetpack, so we don't have to worry about it. Kinetic final. That's what we're trying to find down here. The potential final, well, you're on the ground, so your height would be 0, and therefore your potential energy is 0. So your final kinetic energy is going to be 1.96 joules. What do we do with that? Well, if they want the velocity, I'm going to tell you, you're always going to have to use this equation. Why? It's the only one that has velocity in it. So the mass is 0.1. We're solving for the velocity squared divided by 2, and our kinetic energy was equal to 1.96. So easiest way to do this, probably going to multiply up that 2. Okay, so we have 0.1 v squared equals 3.92. So now we're going to divide by 0.1, divide by 0.1. So v squared is equal to 39.2, and then we're going to take the square root of that. So we get 6.26. Oops, hang on. Oh, mess. Hold on. Okay, so 6.26 meters per second. All right, and that takes care of that answer. Okay. Now it says in the next question, now assume you would lose 0.5 joules of mechanical energy due to friction. How fast would the marble be going now? Well, let's write our equation because we're still comparing 2 points. Ki plus Pi plus work equals Kf plus Pf. Okay. Kinetic energy at the top is still 0 plus. This is still 1.96. That didn't change. The only thing that's going to change is they said 0.5 joules of mechanical energy are lost. So our work is negative 0.5. You lost that. Equals, we're going to do the exact same thing. We're once again going to solve for our kinetic final. And our potential is still going to be 0. So it's almost the same problem, just with 0.5 kilogram or 0.5 joules less of energy. So we do that. We do 1.96 minus 0.5. We get 1.46 equals your kinetic final. And they're asked for the velocity, so you're just going to go, all right, kinetic energy is equal to mv squared divided by 2. And, oops, I make mistakes. Okay, 1.46 equals our mass, which was 0.1, right? V squared divided by 2. And 1.46 times 2 is 2.92 equals 0.1 v squared. Divide that 0.1. And 29.2 equals v squared. And now you're going to take the square root of the answer. And you get 5.4 meters per second. Sorry if that was a little fast, guys. I have jury duty early in the morning and I'm exhausted. So I'm trying to do these real quick. All right, that one's done. Now, the question also asks, the next question asks, where did that mechanical energy go? Like, where was this lost? So when you lost, quote unquote, lost this energy, where did it go? Well, the mechanical energy is not truly gone, okay? It's no longer mechanical energy, but it's turned into things like thermal energy, rotational energy, stuff like that. So it is no longer mechanical energy, but it's not like it's lost to the universe. It's just been turned into something else. Okay, let's say that in this problem now you have a sweet Ford truck, vroom, vroom. Okay, and you're going along, and originally you're going 15 meters per second, so vroom. And now you're going to hit the gas, you're going to do 20,000 joules of work, okay, to speed up the car. How fast are you going now? So slow, more, faster. How fast? That's the whole question in a nutshell. So we're going to do that math, and we're going to assume there's no friction or air resistance, which is unrealistic, but whatever. You probably wouldn't take a vintage Ford car or a Ford truck out mudding anyway. So this whole thing's unrealistic. Let's do it. So we're comparing an object at two different positions. So we're going to use Ki plus Pi plus work equals Kf plus Pf. Originally, we don't know how much the kinetic energy is originally, but we could find it. The original potential is going to be 0 because we're on the ground. The work, they told us, they said it was 20,000 joules. Kf, that would be kind of helpful to know. If we know this, then we can find the final velocity. So that's really our goal. And our potential final will be 0 because it hasn't said anything about changing the height or anything like that. So the potential energy is staying the same. So let's go after this kinetic initial. So Ki is equal to mv squared divided by 2. So Ki is equal to, the mass of our truck is 1,000, which is pretty low for a truck, but whatever. V squared, 15 squared divided by 2. Remember, the squared only applies to the 15. You don't do 1,000 times 15 squared. You just do 15 squared. Then you're going to multiply that by 1,000. And we get this for our initial kinetic energy. Big number. Joules, units. All right, so we're going to plug that back in. 112,500 plus our work was 20,000 equals our K final. So we're going to add those together, and we get this big honking number here. Okay, what can we do with that? Well, we can use it to find our velocity by doing mv squared divided by 2. So we can plug it in. 132,500 equals our mass was again 1,000. V squared divided by 2. I think the easiest in this situation is to do 1,000 divided by 2. So 132,500 equals 500 V squared. So we're going to divide by 500 on both sides. And we get 265 equals V squared. So we're going to take the square root of 265 equals V. And we get 16.3 meters per second. So even though it seemed like a lot of joules were being added, we got a lot of mass going on. So really we didn't change our speed that much. Okay, last one, we have this elevator, and this elevator is going to be moving up. You're going to start, come here you. This elevator is not going well. Sorry, I had to move things. Hopefully it works now. So I'm going to take my elevator and I'm going to move it up 3 stories, which is 10 meters. And the question is, how much work is going to happen when you do that? Assume no friction, air resistance. Again, no friction, no air resistance. Pretty unrealistic. We do have one mass that we're comparing in 2 different positions. So we're going to use Ki plus Pi plus work equals Kf plus Pf. The elevator, when you are at the bottom, at the top is stopped. It's not like you jump into a moving elevator like some sort of superhero. I mean, unless you are literally Spider-Man, in which case I would really like to see you outside of school so that you can share your powers with me. That would be pretty amazing. I already have like a superhero name picked out, so let's talk. Okay, so you have Ki would be 0. Kf would be 0 because you're stopped. Again, unless you're Spider-Man. The potential initial at the bottom would be 0. And potential final would be really helpful to know right now. Notice how many of these things turn into 0. A lot of these problems, a lot of stuff goes to 0. So don't be weirded out if that happens to you. So if we knew that potential final, we'd pretty much have this thing in the bag. So let's calculate that. So potential final, P final, would be mass times gravity times your height at the end. So potential final is, our mass was 800. Gravity is 9.8. The height was, don't put 3 because it says 3 stories just to throw you off. The height was 10. So our P final is 78400 joules. And let's plug that in, see what happens. So work equals 78400 because that was our final potential. And that's it. We're done. Box it up. It's Physics Christmas. That was a lot of problems. Good for you if you stuck through this whole thing.